So we already saw a preview of this section in the previous section. So if you remember, I was graphing with technology, with Maple, to show a three-dimensional picture of a curve, which is what a vector valued function will always be. A vector valued function will always graph as a curve. And the reason I was doing that is because it's really hard to graph in 3 dimensions and have a sense of what you're looking at. We are not Michelangelo's here. We are not Leonardo da Vinci. It's going to be tricky for us to draw in 3 dimensions. Artists spend years and years learning how to do it well. Now, that said, there are a few cases that are actually okay. They're pretty easy to draw, and we can manage them by hand. So that's what we're going to do first. So we're going to draw some things by hand, and we're going to back ourselves up with Maple, and we'll draw them both ways. All right, now the simplest case is when one of the components is a constant. So if you see this here, one of the function components is a constant. So because in that case, what you're really drawing is a 2-dimensional graph on some plane that is shown by that designated constant component. So for example, in this particular one, you can see that z is 5, which is a constant. And we already saw in a previous section what that looks like. Z equals 5 is what, 1, 2, 3, 4, 5 right there. It's a floating carpet. Right? It's some plane that's parallel to the xy plane. So our curve will lies on the plane z equals 5, which is parallel to the xy plane. All right, now what's the curve going to look like? Well, to know that, you have to look at the other 2 components. And if we look at those, little bells should be going off on our head. We know what those are. That's a circle, right? If x is 2 cosine of t and y is 2 sine of t, that is a circle. It will have a radius of 2. And it'll be rotating counterclockwise because we have cosine then sine. So counterclockwise, because of course we need direction on these. They're like parametric functions. And it'll have a center at the dot I already drew, which is 0, 0, 5. So this is not to scale, so bear with me here. But we're going to have a circle going around here. It's going to be moving counterclockwise. So if this is the x-axis and this is the y-axis, that means it's going this way around. And it has a radius of 5. Oh, sorry, a radius of 2. My bad. It has a center of 0, 0, 5, and it has a radius of 2. Well, that wasn't too bad, but let's look at it in Maple just so we can see. So in Maple, I'm using implicit plot 3D, and I'm telling it to graph z equals 5, and then I'm giving it grid notation. So I'm saying, hey, make this graph from -3 to 3 for the x, -3 to 3 for the y, and then the z equals 0 to 6. So it's graphing that plane. I made it yellow in color. I made it have a style that's a surface style, so it doesn't have a grid pattern on it because I wanted to be able to see. So I could also add some transparency to it, which I didn't, but I could say, hey, make it a little bit see-through. Transparency equals 0.25. And so if I do that, and then I have to rerun this, there's S1, then it's going to take it a second. Oh, whoops, I didn't load with plots. Sorry. If you don't load with plots, it's going to give you an error. And then I spelled transparency wrong, which is why it's giving me that error. There we go. Now it's fine. I've actually hidden the outputs. I put colons after them, so it's hiding them, so I don't need to see them. This piece would give me the yellow plane. This right here is the space curve. This is what I'm trying to graph, which is that circular curve. So I type it in, space curve as a command, and then I told it the curve, right, the vector valued function, and then I told it what I wanted to go from. So I want one distance around, so 0 to 2 pi. I made it blue, and then I made it have a thickness. If you don't, it can be really hard to see these things. And then what I did was I named my plots. So P1 is that plot and S1 is that plot, space curve plot. And then they're there, right? If I uncolon them, you can actually see them there. That's what it looks like. But I don't want that. So I'm just going to put the colon in, and then I use the display command to put both of them together on one graph, and I can see them. All right, there we go. It's as simple as that. So let's look at another one. We have 3 sine t, 4j, and 3 cosine t k, or 3 sine t I should say. All right, so you'll notice that the j component is fixed. So y equals 4 is a constant. So that means that the curve lies on the y equals 4 plane, which is parallel to the xz plane. So if I go out here, 1, 2, 3, 4, right, there's my dot. And to show the parallelness, I don't know how to say that, I try to draw it kind of parallel to the x-axis, parallel to the z-axis, parallel to the x-axis, and so on, like that. All right, so this plane is out here. And then what have we got? What's our curve? Well, I see 3 sine t, right? So x is 3 sine t, and y, or y is 4, sorry, z is 3 cosine t. That's a circle. That's a circle, radius 3 this time, and it's going clockwise because it has the sine in that x component. And then its center is at 0, 3, oh, excuse me, 0, 4. I forgot what constant. 0, 4, 0. So it's that point right there, and we have a circle going around. Like that. It's not a great circle, but we're making it work, right? Because of course it's tilted because it's on this plane. So this is the y equals 4 plane, and we have our circle going around in a clockwise direction. This was the z equals 5 plane up here, if you want to put that in. Oh, and just for fun, let's go back to Maple. And I did the same kind of thing. So I said, hey, Maple, you know, draw me this graph, right? And actually, I think I will put in some transparency 1 second. There, and I increased my grid just a little bit so we could see it a little better. So there it is. There's the circle. And we're looking at the shadow. So on the back side, there's the front side. So you can see it's on that plane and it's a circle. It doesn't show the motion. That's something you just have to know. You have to know that it's moving clockwise, which it is. Again, I graphed the plane with an implicit plot command, and I'm graphing the curve with a space curve command. I named them both, and I'm just displaying them. Easy as that. All right, let's look at this third one here. We have 3 comma t squared. So this is going to be easy to draw because x equals 3 is constant. So that means the curve lies on the plane x equals 3, which is parallel to the YZ plane, right? Which is very easy to draw. So we like this one because x equals 1, 2, 3. I mean, it's hard to get depth, but again, I try to draw parallel to the other 2 axes so you can see. So there's your plane, like that. This is x equals 3. It's like a window that you're looking through. All right, so then what's the curve? Well, for once, it's not a circle. So let's look at that. So y is equal to t, and z is equal to t squared. So what would that be? Let's just put that together in a little bit in your head. I mean, I can graph it in Desmos if I need to, but just think about this for a second. If z is t squared and that's y, then doesn't that mean that z would be equal to y squared? That's a parabola. That's a parabola. Oops, not parabola. Parabola in the plane x equals 3. Right? It would have vertex 3, 0, 0. So here's 3, 0, 0. So it's going to be a parabola. And it's going to move, right? It has an orientation, right? So if you think of low values of t, so -4, -3, -2, -1, that would be over here, and then it's going to move this way as you come through. So it's a parabola in the plane with vertex this that has an orientation that moves from the negative y to the positive y, right? The negative y to positive y. Right? It's moving from the left to the right if you're looking at the yz plane. Or in this case, the x equals 3 plane. Right? So if you look directly at the x equals 3, which of course we are, you can see that it's moving from the left to the right. All right, so now let's double check ourselves. So I've got my space curve. Well, I've got my implicit plot here, which is my x equals 3 plane. And then I've got my space curve right there. And I made it have some thickness so I could see it. Again, I'm going to put in some transparency right here, if I can spell it right. So transparency goes from 0, which is no transparency at all, which is what you're seeing currently, to 1, which makes it completely see-through. So the lower the number you choose, the less transparent it is. But that way I can just kind of see the plane, but I can see it's kind of sitting in the plane. All right, so that's how to draw a picture on a two-dimensional. In a way, it's three-dimensional, but you're kind of faking it into two-dimensional because one of the values is fixed.